Okay, thank you, Kevin, for the introduction, and thank you, Mathieu, for the invitation. I will continue to speak about plasmonics, but not localized plasmonics as already explained before, and very interesting, but on non-localized surface plasmonics, which is main application. So they are beautiful, greatly propagated in SSE14 and platform. And I will speak about it with two main parts, actually. I will quickly introduce surface plasmon, and I will focus on surface plasmon polarizer. And two examples, plasmonic resonance for SPR sensors. We are developing using metal surface, corrugated metal surface, which is rating-based surface plasmon resonance. And another interesting effect of this kind metal surface to explain extraordinary optical transmission. And I have some banknotes to this exploit this effect. Okay. Okay, so quickly I will introduce surface plasmon, but just it has been well explained, so I will explain the difference between localized and non-localized surface plasmon. Here it is a question of distance and length of interface. In both cases, we need metallic medium and dielectric medium. So if we reduce the size of this interface, we put surface plasmon resonance and localized surface plasmon resonance. So it is the same effect. It is oscillation of free electrons, which oscillate at certain frequencies, and we have electric field, which is at the interface of the metal and the dielectric. And we consider two approach. It is the surface plasmon polaritons. It is an evanescent field, which will propagate like a wave at the interface. It is the propagation with attenuation of the electric field in the propagation distance and also in the medium, mainly in the dielectric. And here it is a concentrated electric field around the nanoparticles. So if the dimension increase, we will go from one side or to another side. Of course, the electric field here is more concentrated. The value of this electric field is much more higher than this than here. It's easily explained. And now I will concentrate, I will focus on this kind of surface plasmon, what we call surface plasmon resonance or surface plasmon polariton. And as it has been explained just before, when we consider this kind of surface plasmon resonance, we consider most of the time the reflection of the reflected beam, and we consider the attenuation of the dip in the reflection due to the absorption of the surface plasmon resonance. And here, as Olivier explained, we consider mainly the absorption of the particle, of the nanoparticles, which depends on the size, the nature, the interaction, a lot of things to give rise to color effect. Okay, so let's consider this kind of surface plasmon polariton. And here we have a propagation wave along the surface, and we will consider the electric field, and I will introduce slowly the interest of this kind of things for a sensor. So let's consider this interface, dielectric and metal. It is a localized collective oscillation of electrons, which will rise to a surface wave, and there are key parameters we define, and it is very important for sensing. It is the condition on the permittivity. The permittivity must be of the metal is negative, and it must be higher than the permittivity of the dielectric medium. And here, in this case, we can consider a surface plasmon with this constant propagation. We consider mainly the real parts for a quick approximation, but there is also imaginary parts, and it propagates like this. And we will define this length of propagation, and it depends on the permittivity of the dielectric of the metal, and of course of the wavelength. And also we will define something very important for sensing. It is the penetration length in the dielectric part and in the metallic part. So it is very different. There is much more the distance in the dielectric. It's much more higher than the distance in the metallic part. But it is very important because it is what we will consider for sensing. And of course, the refractive index or the effective index of the plasmon is slightly larger than the refractive index of the dielectric in the case of the dielectric, which is air. Okay, so it's not enough. We define the surface plasmon, the wave, the key parameters, but we need to excitate what we call the excitation of the surface plasmon, because it doesn't exist if we have only incidence beam here like this. We need something else to have this, what we call this phase matching between the propagation constant of the plasmon and the K vector of the incident beam. So there are several configurations. The main configuration is what we call Fleischmann configuration. We add a prism to have this phase matching between the incident beam with the prism and the K vector of the surface plasmon. And here we have this resonance condition, and we can excite the plasmon. But here we will consider mainly, in my talk, I will consider gratings. It's not often used, I have to say. We will excite the surface plasmon with a diffracted order, which is evanescent. And we will have this phase matching between the propagation constant of the plasmon and the diffraction order. Okay, so we will now focus on gratings, metallic surface, corrugated periodic gratings. And in this case, we will have to consider the period of the grating, the incident beam, and the depth of the grating. And most of the time for plasmonics effect, we consider a perfect sinus profile of the grating. Here we can excite the plasmon with this constant propagation with a -1 diffracted order to couple the surface plasmon resonance. In this case, we have a dip in the reflection for a certain long wavelength, which will allows us to excite the surface plasmon resonance. The resonance of this, the wavelength, the resonance is fixed by the permittivity and also the period of the grating. So we adjust everything to work well. And here you have the intensity of the electric field during the scan of the incident beam. Okay, so in more details, we excite the plasmon with the incident beam. We can define its K vector. And here, for sensing, what is important is that this electric field, which is evanescent in the, let's say, several nanometer. It depends on the wavelength, but it is in the order of the wavelength. So it is like an antenna, or what I call it is like a noise, which will sense everything which will happen in this interface. The maximum is it at the interface metal dielectric. It depends on the permittivity, so it's very good because we can change the permittivity. It will change the propagation constant of the plasma, and it is what we use for sensing. So let's explain in more details. We have this resonance, and when we change the refractive index, the permittivity, it will move we will shift the resonance, as Olivier explained, also for nanoparticles. But here we have to scan or to follow the peak of the wavelength, or it can be also with the angular spectrum. Okay, but it's not finished for sensing. We know that we play with the permittivity of the interface metal dielectric, but if we want to fabricate a sensor, we will use what we call on the gold surface a functionalized layer. There are two main approaches, a bulk layer for gas detection mainly, and this functionalized layer will absorb, or we will have a chemical reaction which will change the refractive index or the permittivity, or in the case of biomolecules detection, we will functionalize with a chemical linker to have this kind of binding of the target molecules. It will change in both cases the resonance. Okay, so it exists for a long time, a lot of sensors exploiting this approach. Just a few words about SPR sensor. It started in the 90s, so with first demonstrator, and now it still continues to increase. So I think it's a very promising approach for the selectivity and for its high performance in terms of sensitivity. A lot of instruments, more or less miniaturized, and the most well-known analyzer is the P-Hacker system with several channels for microfluidics. Now, a lot of people work on it. We're changing the approach for the detection, with EA also, a lot of combination on the functional layer. The most important is selectivity and sensitivity. Here I would like to introduce our approach, which is, I would say, completely different, slightly different from the state of the art. We use diffraction gratings as for sensing, and this phenomenon, which we call switching effect, has been, I would say, discovered or seen during a PhD thesis of Jean Soras Vincent more than 10 years ago, and he was playing with what I will explain later on the extraordinary optical transmission, and he played with the period of the grating and the depth of the grating to see how the efficiency of the diffracted order change. And we saw a very interesting effect. Yes, it is difficult to understand. I will explain later. It is the efficiency of diffraction gratings of the -1 and the 0, the -1 and the 0. And we see here energy transfer between two propagative diffracted order. Okay, so let's explain in more details. Here you have what happened when we change the depth of the gratings. When we change the depth of the grating here, we have the efficiency of 0 and -1 order with a modification in the efficiency. And for a certain depth of the grating here, we have almost energy transfer. We call this a switch effect. So it was very interesting. We don't know at the moment what to do with this. Here you have more animation which explains with the direct space what happened. You have here the incident beam, the 0th order, and the -1, and you can see as a function of the incidence angle, the efficiency is completely different. And for this, almost quite significant. Because I explained just before, when you excite the surface plasma, here, this is the case, energy is absolute, right? Surface plasma. In this case, it's completely different. So it is what we call a lossless surface plasma resonance. Because here we excite the plasma, but the energy is used for the one of the propagation effective order. So it's strange. So we work on it. Olivier Barriot and a colleague, Sasha Tishenko, worked on it to explain this phenomena, and it was well explained with a couple mode analysis. And we now how it works and how to exploit this. Here, once again, we have to understand that in this case, we excite with the incident beams a surface plasma resonance. Okay? But interaction of the surface plasma resonance, which propagates along the grating, will interfere and interact with the propagative diffractive order, either the 0 or the -1, to, let's say, give his energy, because the interaction is so strong. And why it's so strong? Because we work with what we call, in my community of grating, it is the strong grating, because the depth of grating is very high. We have a strong interaction which can explain the energy transfer. Okay, so it worked, we are happy. And 6 years after this explanation, we think about this configuration to develop a sensor. Here you have, if you remember the shape of this switch effect, and when we change the refractive index, since the surface plasma here are excited and interact with the propagative order, when we change the refractive index, it changes slope. So good, you see, and with this phenomena, we said, okay, let's use it for a sensor. And here, if we stay at one angle, let's say the second crossing point, where the efficiency are equal, you see, for the two diffractive order. And when the refractive index or the permittivity is changing, we perform the difference of the efficiency. So it is the explanation is, I would say, perhaps difficult, but to use as a sensor, it's very simple and easy to understand. So the sensor looks like this. We have gratings with the good design. We have a laser diode, a TM polarized laser diode, and 2 detectors at the crossing point. And with a functionalized layer, either a FIC or with biomolecules, we stay at one angle. For example, here, we have this evanescent field, which will sense what's happened at the surface. We develop the sensor, and we measure to get the performances of the sensor. We developed this setup with Hugo Bruyère. He was the first PhD student who worked on this sensor. So he worked on the proof of concept, let's say, in vacuum. So here we measure the two efficiency. We perform the difference. We measure this difference as a function of as a function of pressure, because the refractive index depends on the pressure, and we can calibrate our sensor in terms of LOD. So it means in terms of what it is possible to measure in variation considering the refractive index. And we achieve 10⁻⁷ refractive index unit. It is in the state of the art. So, okay, continue developed sensor for hydrogen detection. It is the CAPTI project with using a palladium layer. It's well known. The interaction between hydrogen and palladium layer will make the layer change as a hybrid phase, and it will change the permittivity. Okay, just a few words about the fabrication. The fabrication of the grating, we use laser interference lithography on photoresin, and we use the process of nano imprint. So we take a copy of this photoresist-based gratings, a copy, and then this copy in PDMS is used to imprint functionalized layer, and we have our gratings, and then we deposit a gold layer and palladium layer. Here you have the analysis of the gratings and FFT analysis of the IFM profile give us almost one peak to be sure that we have the science ratings. Here it is the experimental setup for hydrogen, and let's go to the limit of detection. We are below the ppb after signal processing. Okay. Okay, so let's move to another application, which is the extraordinary optical transmission. We know that if we have an incidence beam on a flat metallic surface, no signals go through the layer of the metallic film. If we corrugate the metallic film, we will have an extraordinary optical transmission. And we will explain. There are applications in the optical security element, in polarizer, in all optical sensors. Let's come back to this, what I explained in details before. It is the excitation of the surface plasmon. And I like to make the analogy with resonant waveguide grating. So we don't speak at all about metallic. Here it is pure dielectric. But there is a kind of analogy because when we spoke about resonant waveguide grating, we have an incident beam. We excite a mode in the dielectric waveguide, and it will interact with the incident beam to give rise to a resonant reflection. So it's difficult to understand why we have a resonant reflection in a transparent medium, but it works. It is explained. So here you have a beautiful application. When you look at your identity card or your passport, it is a resonant reflection to give this red and green color. So what is the link here? For a moment, no. But if we reduce the size of the grating of the metallic layer, we will have this kind of resonant transmission. And it is what we call extraordinary optical transmission, like what we call the resonant reflection for a waveguide grating. It is quite easily explained. If we consider first a metallic layer, a thin metallic layer, for both polarization, you have almost 100 reflection for T and TML. For a non-dilated periodic metallic layer, for the T, you will have almost 100% of reflection. For the TM, we can expect to have 80, let's say 90% of reflection. So it is a citation of the surface plasmon. It is the same what I used before. If we look in details of this at this layer, thin layer, we will actually excite two surface plasmon resonance at both sides of this thin metal plane. Of course, it works for a certain, if the layer is too thick, it doesn't work. But here you have this kind of transmission And there is an overlap of the two surface plasmon resonance, and it will give rise to what we call two modes, the long range and the short range, an asymmetric mode and a symmetric mode. It is the schematically the electric field distribution for each plasma. The effective index of these two modes is different. So it is the reason why we have one wavelength for the long range plasma and another wavelength of transmission for the short range plasma. It is the short range plasma, since it is centered in the metallic layer, is more lossy. So it's the reason why we have less transmission. So we also did fabricate a demonstrator for color transmission with metallic grating embedded in a plastic foil, and to have this kind of effect, of color effect. Here it is the SEM analysis of the grating embedded in a plastic foil. We work with hologram industry, and hologram industry changed to series, and now I see it is in group in a close collaboration more than 10 years ago. And we could explain that we have different effects using this extraordinary optical transmission, because I didn't say, but it is very sensitive in the color, the wavelength is very sensitive to the angle in the collinear incidence, whereas it is almost not sensitive in the conical incidence. So we can play by tilting in different ways according to the grating line's direction to have this kind of change in color. So it works quite well. And here it's a pleasure for me to show you this kind of demonstrator, which has been transferred to banknotes in Kazakhstan and Philippines. So thank you, Julia. Thank you, Julia from InBook, who brought me these samples. So you can have a look. You have two kinds of banknotes with window, with a metallic layer, and you can see in transmission. Okay. So, thank you again, Julia. Okay, so to conclude, I present two main application concerning metallic layer, corrugated and, let's say, diffraction gratings for sensing. So we still have a lot of work to develop our sensor. So we work on hydrogen, P-phase, and biomolecule detection, but we are still at the level of demonstrator. And here it's also a pleasure to see that the extraordinary optical transmission get to banknotes in some countries. So it is a good achievement. I did not speak about grating fabrication process. I think it's very important to also address this problem, not this problem, but this aspect, because it's important to have very good grating fabrication processes, and I'm convinced that it's good to work on nano-imprint lithography to have low-cost alcohol processing. And I would like to thank you.